This is the dcdc converter I ended up building after I couldn't find a single commercial module that had everything I needed. I tried a lot of the shelf modules, but every time something was missing. Some couldn't deliver enough current, others had a very limited output voltage, and some simply didn't have the features I was looking for. So I sat down and wrote a list of all the features I wanted in a converter. The real question is, does my converter actually meet all those requirements? To find out, I had to design a PCB, choose the right controller, optimize the layout, and do lots of testing. Now, since one of my main goals was a wide input and output voltage range, the first design decision was choosing the right topology. We know that a buck converter can only step the voltage down, and a boost converter can only step up, so the buck boost topology was the more appropriate choice. It can give us more freedom on the input source because the output voltage can be higher, lower, or even close to the input voltage. Also, a feature I really wanted was digital control. Instead of adjusting the output voltage or current with your traditional potentiometer, I wanted to set them directly from a microcontroller, just like you will do with the programmable power supply. Not only is it much more precise, but also makes the converter easier to automate. So before talking about how I built it, let's see if it actually works. First, to control the converter, I'm using the I2C interface of an Arduino. And because I wanted something a bit more visually appealing than just serial commands, I also built this simple user interface. With this interface I can turn on or off the converter, adjust the output voltage, and set the output current limit. Now, one of my requirements was having a wide output voltage range, and this converter can in fact go from 1 volt all the way up to 24 volt in 10 mV steps. Not only that, it can reach up to 48 volt with 20 mV resolution. So whether I need the 3.3 volt for a microcontroller or 24 volt for a motor, I don't need a different converter each time. Input voltage side, it's all fine from 3.5 volt up to 32 volt. Now what about the current? Well, the maximum output current isn't fixed. It depends on both the output voltage and how much power the input source can provide. Like, you can't draw 10 amp from a puny 9 volt battery, but with a proper power supply, the converter can deliver at least 5 amp across the entire output voltage range. I'm also satisfied with the efficiency performance of the converter, reaching over 90% under certain input and output conditions. In the end, I'm really happy with the PCB I came out with, and if it looks so good, it's also thanks to PCBWay, the sponsor of this video. PCBWay produces high quality PCBs, and until the end of this month they are also offering free solder mask for some of their colors. They can also take care of the assembly for you and offer 3D printing and CNC machining with tons of material to choose with. Just check PCBWay.com, link in the description. So what controller IC did I end up using? Actually, finding a controller that could satisfy all my requirements turned out to be much harder than expected. In particular, there are very few controller ICs that support digital control. Most of the buck boost converters out there rely on the classic feedback resistor divider to set the output voltage. But after comparing many different options, I settled on the LM51772, a buck boost controller with I2C interface. Since this is a controller, it has not integrated MOSFETs. Anyway, there are a few other features worth mentioning. The first one is cable drop compensation. When enabled, it slightly increases the output voltage as the load current increases, compensating for the voltage drop in the cables. The IC also features input voltage detection, where I can set the rising and falling threshold to control when the converter turns on or off. There is also an output discharge function and an external open drain pin that I can use to monitor the converter status. If you want more info, you can check my previous video that uses the same integrated circuit just with the older board that eventually failed. Now, this IC here is an absolute beast, but it comes with a major downside: a 123-page datasheet. It's not like your puny MP3608 with only 8 pages. And they say that I don't read enough books. What a joke. But if you want to design using this IC, you of course have to read the datasheet. Thankfully, there are at least 3 tools you can use to make the design process easier. The first one is Webench. This is basically the fastest way to get a first idea of how the converter should look. You just tell the input and output requirements, and it gives a starting point with suggested components. You can even run simulation with it, and I think it's just a cool tool in general if you want to build dcdc converters. The second tool is the Quick Start Calculator that you can find on the product page. It's basically a spreadsheet that helps you design the converter in much more detail, allow you to calculate and optimize many of the key design parameters. And finally, if you really want to be serious about it, you can buy the Texas Instrument evaluation board. They also provide a user guide with schematic and a complete bill of material, and more importantly, design files, which are a really good reference. Of course, designing a switching converter like this requires a lot more effort than your typical 6-pin regulator, especially once you take all the controller features into account. And covering every design decision will easily serve a dedicated video. Tell me if you want one. Once you have a good understanding of the controller and a solid starting point, it's finally time to start designing the converter. From there, it's all about understanding the pin functions, drawing the schematic, selecting the right components, and eventually turning everything into a PCB. And don't be afraid to fail, this was actually the second version I made. In the first one, I used the wrong MOSFETs, which caused the board to heat up much faster than expected. But that's part of the learning process, every mistake teaches something. And in the end, the converter is working great. Well, that's the end for today. Hope you enjoyed, and see you next time.